Hello everybody, let us continue our lecture series in this course optimal control guidance and estimation. We are here at lecture number 5 where you are talking about some sort of overview of static optimization, and this is part 2 of the lecture actually. So, very quickly we can just see what all we discussed in the last lecture before coming to this one actually. So, we talked about some sort of unconstrained optimization followed by some constraint optimization with equality constraints and then saw some numerical examples on the way. So, these are all what we discussed. Getting motivated from a simple curve sort of thing, and then analyzing those points, and then finally analyzing whether the derivative is 0 or not. It turns out after rigorous analysis through Taylor series that the first derivative needs to be 0. Then we continued further with second derivative, third derivative and so on, and it just turns out that for necessary conditions all odd derivatives needs to be 0, and for sufficiency condition can be arrived at with even powers and all that with the sign sensitivity of that. So, all these things we have discussed in the last lecture anyway. And we saw some examples on the way, then followed to this vector case where the decision variables are actually x 1 to x n number of variables, and in that case you have to define some gradient vector and then Hessian matrix, things like that. And again they are using the same idea of Taylor series, and then we arrived at a conclusion that okay, if for the necessary condition the gradient vector needs to be 0, and sufficiency condition can be arrived by looking at the positive definiteness or negative definiteness of this Hessian matrix actually, and again followed with some examples and all that way. Then we moved on to some constraint optimization with equality constraint, and then we told that okay, this particular problem, the minimize j of x subject to this f of x equal to 0 is equivalent to minimizing this j bar of x and lambda, where both x and lambda are considered as free variable. You construct this function and then use the analysis tools that you know for unconstrained optimization for j bar. We did that and then came up with these two necessary conditions again, and so went through these example problems. And finally, we went some sufficiency condition as well, and told that okay, you have to construct this kind of a matrix and then see the determinant and interpret that as a function of only sigmas, and analyze the sign sensitivity of all these sigmas actually. If all of them happens to be positive, then it leads to a minimum condition, and all of them happens to be negative, then it is a maximum condition actually. Again we demonstrated that using some examples and all that actually. All right, and then we had a good example at the end where we took out this x 1 minus x 2 square, and then constraint was also a kind of a nonlinear equation, and it will ended up some multiple cases, and depending on each of the cases we have to analyze this particular equation. And in the using that case 1, what we got here, we got some results that sigma equal to minus 3, and then hence that leads to maximum and all that actually. So, for considering analyzing all these things for all the roots, we had a conclusion that these two will lead to maximum and these two lead to minimum. Okay, and if you really want to have a global maximum and global minimum ideas, then at this point you have to evaluate the j, both the points, and whichever j happens to be maximum is the global maximum, and within these two you can evaluate the function j, and whichever happens to be minimum happens to be the global minimum. So, that was the idea there actually. Then we had some references, and then I suggested to look at some books and all that actually. So, that was our last lecture. Now, coming to this particular lecture, we will talk about constraint optimization with mainly inequality constraints, and also before moving on, we will also have a glimpse of small glimpse of numerical optimization techniques, especially this steepest descent method and this Newton search, line search, like that actually we will see something. So, those are the things backbone of any optimization technique, including dynamic optimization, that means optimal control areas. So, we will just have a glimpse of it, but again this is not a course on static optimization. So, we will not dwindle over there, we will not take a lot of time to kind of analyze various techniques and all that, but at least good to have some idea of what is numerical optimization actually, and then we will follow up with some numerical examples before winding up this lecture. All right. So, constraint optimization with inequality constraints, that is what we want to see first analytically, and then we will see some numerical things and all towards the end of this lecture actually. So, one very quick way of an inequality constraint approach, or rather I will call that as a naive approach, is something like this. We can visualize a problem where this variable, decision variables, all of them are constrained like this, let us say. So, all of x I or x 1, x 2, x 3, all that are constrained between their corresponding minimum and maximum values. Okay. Then how do you handle that problem? Okay. One easy idea or rather naive approach turns out to be like, okay, you will construct some, I mean you just replace this xi as something like this, where xi, I mean now you interpret alpha I as a free variable. Okay. That means, if no matter whatever is the value of alpha I, note that sin square alpha I is always bounded between 0 and 1. So, if it happens to be 0, then xi turns out to be minimum, and if happens to be 1, then it turns out to be, okay, these two will cancel out and it will turn out to be maximum value. So, no matter whatever is the value of alpha I, you will your xi will be bounded between these two things actually. So, that is the one idea, but also note that we have actually introduced a nonlinear transformation here. That means, xi and alpha I are not really linearly related, and you have this humongous problem of like so many local variables, I mean so many values of alpha I, which will give you to that actually, because sin square alpha I is not I mean it is not uniquely valued, and I mean it is not a unique function sort of thing in a way. So, we will end up with a huge amount of problem here, because most of the time if you just do it and carry out numerical optimization, which typically we have to do at the end of the day, then it is not a very good way of doing that. Also, if a simple problem can get translated into a very complex problem through this nonlinear transformation, if you want to do it through analytical tools actually. So, this is even though it is a very lucrative approach and you can probably try out at the first go, it is not really a universal solution that you are looking for actually. So, this approach in general does not work. I mean, if you can try out, I mean in a given problem you can try it out, if it works out nothing like that, but in general it does not work out very well actually. So, we are in a process of hunting out for better approaches actually. So, let us see that, I mean first the problem definition. What you really want here is minimize or maximize this j of x. Again the cost function or objective function is always a scalar, but the decision number of free variables can be kind of, I mean n dimensional. That means, you have n number of free variables to choose from in a different combinations and all that. But this particular objective function is now subject to this this constraint g1 or g1 to gm less than equal to 0. Now, remember this also embeds this equality constraint, because you are considering less than equal to 0 here. Okay. If it is equal to 0, okay, then it also satisfies that. So, that means, what we discussed in the previous lecture is equality constraint is kind of embedded over here actually. Okay. But we are talking in more general thing, that means first couple of equations may be equality constraint, but rest of the equations are not really equality, they are inequality constraints in a way actually. Okay. But so, how do you handle that in general? Now, consider, I mean this particular problem that this is less than equal to 0. So, the one approach is to introduce something called slack variables, okay, mu1 to mu m, all are considered as slack variables, to convert the inequality constraints to equality constraints. So, because these are less than 0, so I can always add a number there, okay, and just to make sure that these are positive quantities, I will add it something like mu1 square, mu2 square up to mu m square actually. Okay. So, if I do that, it turns out that it is nothing but an equality constraint problem actually. Okay. Then the idea is to follow the routine procedure for the equality constraints, because we know that how to handle those equality constraints analytically, we can carry further and then proceed further actually. However, note that this, even though it is less than equal to 0, note that we really do not know how far it is away from 0. So, these values of mu1 to mu m are typically not known. I mean even though symbolically it is, you can write it that way, using it for inferring something is not really very nice, because you will not have an idea of these numbers to begin with actually. So, we want some condition which are independent of mu at the final analysis actually. So, let us see whether we can really do that or not actually that way. Anyway, so this is a problem of maximize or minimize j of x now subject to this constraint, which is equality constraint basically. Okay. So, this is what you are doing. So, now if you look at this one and then equality constraint, we know how to handle that. So, first we construct a j bar, and now j bar is a function of x and lambda, but also these mu's are free variables, slack variables actually. Okay. So, this is actually a function of all these quantities x, lambda and mu. Okay. So, this is constructed that way. So, as far as necessary condition is concerned, we have to take partial derivatives with respect to all these variables, okay, x, lambda and mu. x is n-dimensional quantity, whereas lambda and mu, okay, remember lambda and mu are given by dimension of the constraint equations, and that is typically m basically. So, we consider this n derivatives here coming from xi partial derivatives, that has to be equal to 0, and then followed by this del j bar by del lambda j, which is like free variable of lambda, considering that free variable of lambda here. Okay, we talk about that actually. Okay. So, this is the second equation, and then we have a free variable with mu, and that mu turns out to be like this actually, del j bar by del mu j has to be equal to 0. Okay. So, these conditions what you are getting n equations, m equations and m equations, that is n plus 2m equations has to be solved together basically. Then we get the idea there actually. I mean, we will get the solutions what you want to actually. Okay. So, we have to utilize these equations, remember that actually. Now, how do you do that? It's time to analyze a little more. So, this equation let us start with, okay, the second one. So, this turns out to be 0, okay. Hence, g j of x I can write it as negative of mu j square actually. Now, if I multiply both sides with lambda j, I can write it that way, but remember that this particular equation comes handy now, lambda j mu j equal to 0 now. So, what it tells us, this quantity is 0, hence lambda j into g j has to be 0. Okay. Okay, just if I take this equation and get g j x is negative mu j square, multiply both sides with lambda j, and then use the third equation what I am having here. So, once I get that, then it turns out that g j lambda j is nothing but 0. Okay. So, this leads to the conclusion that either lambda j is 0 or g j is 0. Okay. Now, if lambda j is 0, okay, that means the constraint is kind of a inequality, I mean strictly inequality constraint, which means the constraint is not acting. That means it is actually a kind of you can visualize as if the constraint is not there actually. Okay. If lambda j is 0, you do not, because that is coming through this constraint equation, right, but see, because you have a constraint equation, you have that and then it is coming through that. So, if lambda j is 0 for a particular thing, you can visualize very well as if the constraint is not there actually, but that is a mathematical interpretation actually. So, if otherwise g j is equal to 0, that means it is active constraint. Now, if you go back to here, if g j becomes equal to 0, then becomes an active constraint. So, if the problem is I mean either the constraint g j is not there, I mean it is as good as not there, or it acts as a kind of active constraint actually. So, that is the conclusion here, which makes a lot of sense actually. Okay. If the I mean if g j is strictly less than 0, then we can very well forget it actually, and then try to optimize only the cost function that way. But anyway, this is the conclusion here. So, lambda j g j equal to 0, that leads to the conclusion that either lambda j is 0 or g j is 0. That means, putting in English words, if a constraint is strictly an inequality constraint, then the problem can be solved without considering it. Otherwise, the problem can be solved by considering it as a strictly equality constraint sort of thing. Okay. So, that is the conclusion here, but it also gives us a procedure to solve now. Okay, let us see how to do that. Now, notice that this equation has nothing to do with the mu's actually. This equation simply deals with lambdas and g's actually. So, really do not need to know the value of mu's now actually. Alright. So, now to consider this analysis further, okay, let us talk about a single I mean a typical case, a typical maximization problem. I mean remember, this is not a minimization problem we are considering, we are considering a maximization problem, and g j is active, that means g j is equal to 0 actually. Okay. So, how do we conclude in that particular situation what is happening there? Okay. Now, let us assume that x is a point where maximization maximum occurs, maximum of the cost value occurs, and delta x I is a small change in x I direction that causes g j to be strictly negative. That means, the moment I go a little bit in that particular direction, my g j becomes inactive actually. In that situation only you got the optimization, the optimal point basically, if that happens. Okay. Alright. So, at that point the maximum occurs, and in a particular direction delta x I, g j turns out to be strictly negative. That means, it from active constraint it becomes inactive constraint actually. Okay. So, that is the point where maximization occurs. Now, how do you handle, I mean how do or what do you infer from there actually? So, but if you go back to d j, okay, turns out to be like the del j by del x I into delta x I actually. Okay. Remember, it is its g j is active actually. Okay. So, this is del dj is nothing but del j by del xi into delta xi, okay. This is less than 0, okay, since j is a maximum point actually in that sense. And then because this particular direction, any direction I go from that particular thing, this has to decrease, right. That is a free optimization problem, but in a constraint optimization sense it may not happen. We are not allowed to go to one side, but whatever direction you are allowed to go, if you go any direction within that allowable zone, then you are supposed to decrease, I mean the cost function is supposed to decrease basically. So, and then this also becomes true because d of gj is nothing but something like this in that particular direction, turns out to be less than 0 from this inference actually. Gj happens to be less than 0 actually here, okay. So, from that it turns out that this condition is also true here. So, now what do you infer from there actually, okay. So, if these two conditions are true, now let us consider delta xi is a positive quantity, it can very well be negative quantity which is discussed here next. If it is a positive quantity, then what happens, we have to satisfy these conditions anyway. So, that means del j by del xi and del gj by del xi has to be negative quantities, then only these equations will be holding true basically. Okay. Now, if this happens to be a negative quantity, again opposite is true, I mean this both of them has to be positive quantity. Now, the thing to note here is both of them has to be either negative or both of them has to be either positive, okay. That is the conclusion for a maximization problem, remember, okay, that is how it is. Okay. Now, if it is a minimization problem, this sign will alter, this will become positive here, and then your inferences has to be both held to be like kind of a opposite sign each other and all that actually. Now, let us not worry about that, we are considering a maximization problem and this is what happens, okay. Both the things will take the same sign basically. Now, what do you conclude from there? Now, we will go back. See, so far we have been dealing with these two equations, we have never thought about that equation, using that equation so far. So, we will go back to that and see what we can get from there. Now, remember this quantity and this quantity, okay, has to be of same sign basically, that is what we have just discussed actually. Now, going back to this is what we are getting here, okay. So, that means del j by del xi equal to that one, I take that on the other side of the story. And because lambda j, all that I can infer here, lambda j is not a function of x. So, I can take it out from there, and it turns out that this gives us another constraint equation, that this partial derivative and this partial derivative are related to each other through that, okay. But these two quantities are always having same sign and with a negative quantity here, that means lambda j has to be negative, okay. Remember, this analysis told us that these two will always have the same sign, no matter whether the delta xi is positive or negative. So, if it have the same sign and this is a constraint equation with a negative sign, then lambda j has to be negative actually, then only it will satisfy all that. So, this is what it tells us? It tells us that if it is a maximization problem, okay, right, that is right, if it is a maximization problem, then these two, this lambda j has to be negative basically ultimately. Okay. So, this kind of analysis you can do case by case and generalize and things like that. So, that is so as a summary sort of thing, this kind of analysis is called something like, earlier it was known as Kuhn-Tucker condition and some books still follow that, but more popularly nowadays it is known as Karus-Kuhn-Tucker condition. The Karus happens to be an independent researcher actually, and then Kuhn-Tucker derived these conditions, it became popular, and later they realized or I think the Kuhn-Tucker themselves or somebody else in the process of analysis, they realized that Karus has actually developed these conditions as part of his master's thesis, and then the story goes on like that actually. So, then they want to attach his name further and things like that, and the problem here is Karus never published his results, it became part of his thesis only basically. So, somehow it was discovered, otherwise it would have been simply Kuhn-Tucker condition all the time actually. So, that also gives us a clue that whenever you get something, try to publish, do not keep it to yourself that way actually. Anyway, so this is the condition here, which is popularly known as KT conditions now. So, this Karus-Kuhn-Tucker condition happens to be something like that. So, what it tells us? It gives us these two conditions, okay. That means del j by del xi has to be equal to 0 and lambda j gj has to be equal to 0. These are the two equations using which we have to solve for various conditions for lambdas and all that actually, okay. Then for j of x has to be, if it is a minimization problem and this constraint happens to be negative, all less than equal to 0, then lambda j has to be positive, okay. remember these are typical cases. What we have analyzed is actually a maximization problem where this happens to be like that. So, hence we will ended up with that condition actually. Okay. So, if it is this way, we will end up with opposite sign. If it is minimum, all these two happen, I mean just a test to alter actually. Okay. So, depending on whether it is a minimum problem or maximum problem, and depending on whether your constraint is negative or positive, you have the standard results getting on here actually. Okay. So, first of our task is to first solve this thing, these two equations. Okay. Remember, this equation does do not include any mu's. Okay. Now, so we have n plus m equations in terms of n plus m variables. So, it is possible to solve n equations, n variables from states. I mean, rather free variables x 1 to x n. I mean, we still not talk about states actually in general. So, x 1 and x 1, x 2 up to x n is what you are talking as free variables, and then lambdas are coming from because of the constant equation. So, these two set of equation we can solve, get some values for x and lambdas, and then we will go back and try to see whether these conditions are satisfied or not, especially whether constant equation is satisfied and corresponding lambdas are satisfied or not actually. So, they are actually in these conditions are embedded like two set of conditions. One is the constant equation itself has to be satisfied, okay, and then the corresponding lambdas has to satisfy that way also basically. Okay. So, that is the problem there actually. So, some comments on KKT conditions. First of I mean, I already told you about that, but it is all documented here. One should explore all possibilities of the KKT conditions to arrive at appropriate conclusion. Okay. And also remember that KKT conditions are only necessary conditions, they are not sufficiency conditions at all actually. And if you really want sufficiencies, then sufficiency checks demand that some concepts of something called convexity, and the function has to be convex and things like that actually. So, let us see that. So, the concave and convex and concave functions can be defined something like that. This particular, I mean, in a scalar free variable sense, if your f of x can be given like that, then it is something like a convex function, and if it is given like that, it is concave function, and if it is strictly like this, it is strictly convex and it is strictly concave. The whole idea here is if you join these any 2 points of this function, then this line is supposed to lie above this curve actually. Okay. Okay. And if you join any two lines here, this line is completely lying below this function sort of thing actually. Yeah. That is what is written here. A function is called convex if a straight line drawn between any 2 points on the surface generated by the function lies completely above or on the surface basically. At a particular point, it will when it is tangent, it will all lie on the point only that way, but that is a one single point only basically that way. Yeah. And if the line I mean lies strictly above the surface on the other hand, it is called a strictly, I mean if it is strictly lying above this, it is called strictly convex actually. Okay. Remember this, we are talking about two different points. If 2 points happens to be same, then it is a tangent point basically, we are not interested in that actually. Yeah. And just opposite case, if the line lies below the surface, it is called concave, and if it is strictly below, it is strictly concave and all that actually. But how do you do that? How do you analyze that mathematically? That's more important actually. So, that is where this differential geometry and all that comes into picture, and then the conclusion through calculus is something like that actually. Okay. We can always this concavity and convexity are typically governed by the positive definiteness or negative definiteness of Hessian matrix of this f of x actually. Yes, so that means del square f by del x square is contains some sort of a curvature information. That curvature information will give us whether this is convex, concave and all that. The idea is like this, you have a candidate solution x star. So, at that point you can evaluate this one, and if it is a scalar variable, it is just a number, but if in general it is a matrix, we have seen all that actually in previous lectures. So, this particular matrix can be evaluated here, and if it happens to be strictly positive definite, that means all lambdas are strictly positive. Remember, this is actually a symmetric matrix guaranteed to be, and hence the eigenvalues are all real actually. So, if it on top of that, if all happens to be positive number, then it is a positive definite matrix, and it is strictly convex function actually. Yeah. And then it is a positive semi definite, negative definite, negative semi definite, indefinite and all that can be inferred from there just by analyzing the eigenvalues of this matrix, okay, because it is a number after all. This matrix is evaluated at a particular point x star, it is a number. So, you can evaluate all the eigenvalues, and depending on these conditions, whether all of them are positive, strictly positive, things like that, you can infer whether the function is strictly convex, concave and all that at that particular point x star. I mean that is also has to be noted down actually. Okay. and if some of them happens to be in positive, some happens to be negative and all that, you can't talk anything about that. That's in this particular case, it is typically called as indefinite function sort of thing. Alright, so condition for which these Kuhn-Tucker conditions or rather Karush-Kuhn-Tucker conditions are also sufficient turns out to be like this actually. Okay, they are in general they are necessary, but in addition if this kind of combinations are satisfied, then this whatever x star value you are talking about, that happens to be sufficient also basically. Okay. So, what is that? Now, if you are looking for a maximization problem, that means your j of x has to be strictly concave, okay, and all gj's has to be convex, need not be strictly convex. Okay. But for a minimization problem, this j of x has to be strictly convex, but gj has to be convex. So, this constraint equation need not see convex also includes linear equation. Okay, linear equations are straight line sort of representation and all that way, then they are also included in the constant equation basically. Okay. But the cost function is to be strictly concave or strictly convex. That means, it has to be some sort of a I mean quadratic fourth order powers and all that what we talk for minimization or negative of them for maximization and all that. Okay, those will satisfy this kind of conditions actually. Okay, so this is the summary actually. You analyze all that. Okay, let me go back a little bit. You start from something like this. Okay, in a given problem, you formulate these two equations and get some values of all x's, xi's and lambda j's, and then see whether this set of conditions are satisfied together. Okay, for any condition that way. Then if you have, then you if these conditions are satisfied, you have these necessary conditions getting satisfied. Now, we will talk about sufficiency condition. For sufficiency condition, you have to see whether this these two j of x and gj of x satisfy this kind of things. If satisfy, then it's both necessary and sufficient actually. Obviously, it's time for an example to get some ideas clarified and all. So, let us talk about this kind of an example. J of x happens to be x1 square plus x2 square, standard problem to minimize a quadratic function sort of thing. Subject to these two equations now, x1 minus x2 is less than equal to 5, but x1 minus x2 is also greater than equal to 1. That means, this value what you are looking at lies between 1 and 5 basically. Okay. So, in that segment, whatever minimization you talk about, can we derive it analytically actually. Okay. So, what is the first thing? First thing to note, what is Gj, what is G1 and G2 here, and our analysis all tells that we have to do in a negative sense, in the less than equality sense basically. So, first one is easy, so you just talk x1 minus x2 minus 5 is less than equal to 0. The second one you have to change sign, if you put a minus sign here, it becomes less than equal to minus 1, in that sense it is minus x1 plus x2, and remember this is a minus 1 here, so it becomes plus x1, plus 1. So, this is G2 of x has to be less than equal to 0 actually. Okay. So, now we have a standard form, minimize this function, this cost function subject to this G1 less than equal to 0 and G2 less than equal to 0 actually, that is what we are looking at. So, what is the standard thing? First we have to formulate what is J bar, and J bar is nothing but J plus lambda transpose this function G1 G2, that means lambda 1 into G1 plus lambda 2 into G2. Okay. So, that is J bar. J bar is J plus lambda 1 G1 plus lambda 2 G2. Now, we talk about necessary conditions. First is all these partial derivative has to be equal to 0. So, partial derivatives in terms of x and in terms of lambdas and all that we will see that, but that see partial okay, let us go back to that for a recapitulation. All that we are talking is partial derivative with respect to x, and then directly we will go to this condition. This partial derivative with respect to lambdas are not necessary actually, because those conditions have been derived and embedded here in the process of deriving and all that, it has been embedded here actually. So, we do not need that. All that you have to do is partial derivatives with respect to this xi's, and then use this condition directly basically. Okay. So, this is what we are doing here. So, for J bar is there. So, partial derivatives with respect to x1 and x2 will give us this condition, and then lambda 1 G1 equal to 0 and lambda G2 is to be equal to 0. Now, how many equations? 4 equations obviously. How many unknowns? 4 unknowns, x1, x2 and lambda 1, lambda 2. So, we should be able to solve this actually. Okay. But remember, this is not a linear set of equations, even though the equations are linear, but these equations are certainly nonlinear. You can think of them as bilinear and things like that, but then bilinear is also part of nonlinear equation actually. Okay. So, this equation has to be solved, and then we will solve case by case. and then then verify whether this whatever solution candidates you are getting here will get multiple solution candidates, will they satisfy these 4 equations simultaneously or not. If they satisfy, they are part of the necessary conditions and all. So, they are candidate solutions. If they do not satisfy, in other words, one of the conditions not getting satisfied, that means that is not a possible solution actually. Okay. So, that is what you are looking for here. Now, also very quickly you can have you can observe that x 1 is equal to minus x, I mean x 2 equal to minus x 1 here. If I solve x 1 here, it is whatever minus of lambda 1 lambda 2 by 2, and x 2 here is negative of that basically if I solve there. So, that is x 2 is equal to minus x 1. That will quickly give us whether to keep a solution or reject a solution, because if you know x 1 and x 2 and x 1 are just opposite signs, very quickly you can see whether it is happening or not. So, that is just an inference sort of thing actually. So, now if you go back and try to solve case by case, and I certainly encourage you to solve it. First of all, remember how do you go about solving it? Just look at the equation. You are getting either lambda 1 equal to 0 or this is equal to 0. Here it is either lambda 2 equal to 0 or that 2 is equal to 0. Okay. So, with respect to these possible cases, we have to solve it. Okay. So, either lambda 1 equal to 0 or lambda 2 not 0, or lambda 1 0 lambda 2 0, that is also a possibility, and lambda 1 not 0 lambda 2 0 just a possibility, and both of them being not 0 is also a possibility. In that case, if both of them are not 0, then these two has to be equal to 0 either way. Now, in those situations you solve it, go ahead and solve and find out that in this particular case this is the solution, this particular case that is the solution, things like that actually. Now, very quickly you can say, remember this x 1 x 2 equal to minus x 1, right. So, this candidate is not actually, it does not satisfy that, I mean well it satisfies in a trivial sense actually, but okay, let me pick up another one. I think this satisfies that. So, maybe you will not be able to do that, but suppose it is a different number here instead of 0, okay, then it is very easy to kind of utilize this equation and then infer that it is not happening. But anyway, that is not a major point actually. So, you have some values here lambda 1 0, lambda 2 not 0 like that, and corresponding x 1 x 2. Now, go back to these equations and try to see whether that is satisfied or not actually. Now, what is happening here? Lambda 1 equal to 0, lambda 2 not equal to 0. Okay. So, lambda 1 equal to 0 is acceptable. Okay. So, that is not a point, that is not a problem. Lambda 2 equal to 0 is also, I mean not equal to 0 is also a possible candidate, because lambda 2 is can be strictly greater than 0, that is not a point actually. Okay. So, but see this conditions that you are looking for is primarily to evaluate this set of constraints basically, because this condition has been taken care from there also basically. So, look just let us look at these two equations first. So, if you have x 1 half and x 2 minus half, okay, if you put x 1 half and x 2 minus half, okay, and this happens to be minus 5. So, this is less than 0, it is satisfied. And if I have this one the second condition of half and minus half. So, this is plus half and what is that, sorry, one second, x 1 is half and x 2 is minus half basically. So, x 2 is minus half, you put here, it is half here and all that actually. So, this is minus half minus 1 plus 1 is 0 basically. So, this is also satisfied. So, in that situation it is acceptable. So, this is a feasible candidate actually. But it turns out that all other cases, if you if you just do lambda 1 equal to 0, lambda 2 equal to 0 and things like that, then these two equations has to be satisfied and all, you will see that it is kind of not feasible actually, and similarly all these are not feasible. Okay, see that okay. So, if for example, if I take this minus 5 by 2 plus 5 by 2 minus 5 by 2, and I suggest that you do it yourself basically, because I will not spend too much of time here. Just to see that all these feasible conditions you take case by case and try to analyze whether all these conditions are satisfied or not. Very quickly you will see that only one condition it will satisfy, all others will not satisfy for some reason or other actually. Okay. So, that means this is a feasible candidate, x 1 half and x 2 minus half, or other things are not a feasible candidate actually. Now, okay, because this is only condition getting satisfied, you can always tell, okay, sufficiency condition is there in general, that is your intuitive feeling. But if you really want to find out whether it is really sufficient or not, you have to go to that. So, that means j of x equal to x 1 square plus x 2 square, obviously it is strictly convex function, because if you take a second derivative, it will happen to be a diagonal matrix with 2 in the diagonal. So, 2 in the first diagonal entry and 2 in the second diagonal entry actually. So, that means eigenvalues are 2 which are both positive, it is strictly convex actually. And G1 and G2, if you see, this is this G1 and G2 whatever you are talking about, they are all linear equations, and hence they are
I mean convex actually, and we do not need strictly convexity here actually, just convex is good enough actually that way. Hence, this condition Karuskun-Tucker conditions are both necessary and sufficient as well actually. Okay. So, that means this particular case that you are talking about, whatever you are here, okay, is I mean this solution candidate and all that what you are talking about is both necessary and sufficient, and hence it is a candidate solution in both sense. But is it really global? I mean that also happens to be true, because this particular function what you are looking at, okay, del square j by del x square is not a function of x star. That means whatever is your x star what you are talking here, okay, this second order condition what you are talking, I mean what is coming out here is just a function, just a diagonal matrix with 2 in the diagonal. That is not a function of x star. That means no matter whatever is x star, this condition is guaranteed to be satisfied actually. So, that is how you can conclude that it is actually a global minimum also. So, that is how you can the analysis proceeds and things like that actually. Okay. So, this is all about this kind of analytical tools and all that way, how do you go ahead and do that. And remember, we started with a very simple problem here, okay, just a scalar objective function with a simple looking form, subject to just I mean 2 equations with two free variables. And if you really happen to solve it using pen and paper, you will require a longhand algebra to derive all those conditions. And in general, it turns out that is not a very good approach of doing complicated problems actually, complex and complicated problems, because it does not give us a very good analytical hold. In a way, the algebra can be so involved that it may not be possible to do this kind of nice analysis in general actually. So, people have always looked at this numerical optimization approaches, and over the period of time the field has matured quite a lot. That means, you have several numerical algorithms now, which are quite efficient actually. Okay. And also this computer technology is has seen this a lot of improvement over I mean last couple of decades. So, you have a huge amount of computing power as well actually associated with it. Of course, they are not sufficient in optimal control sense in a way, 2-point boundary value problem and all, we will see those are different class of problems altogether. But having said that, advancement of computer technology always help actually, no matter what actually that way. So, and utilizing all these powers together, since then people have started utilizing this online solution of this optimal control problem and all that. We will see all that later. But here we will see some basic ideas of what is this static optimization through numerical methods actually. So, what is the basic philosophy here? Basic philosophy is to kind of we do not know the final solution, we do not want to go there at one shot actually, but we start with some sort of a meaningful initial guess, okay. And trivially I underline this statement because it is a critical thing in practice actually. As far as an algorithm development is concerned, it may not look very important, but in any practice the initial guess value or initial guess solution and all that has to be done carefully. It has to be done in a meaningful sense. In other words, it may not be an optimal solution, but it has to be as close to optimum as possible in general, or if you talk about a control solution, rather it has to be kind of a stable solution to begin with and things like that actually. Okay. So, if you do that, then your iterations and all becomes lesser, your computational load becomes lesser, your convergence properties become better, things like that actually that way. Alright. So, what happens here is you start with a meaningful initial guess. Well, let us denote that as x superscript 1 actually, and then we have to, all that it matters is to find a search direction, because the direction, number of search directions are infinity really, you can go any direction you want actually that way. So, we have to find a meaningful search direction, and let us denote that as pk, okay, p to the p superscript k, and k can be like 1, 2, 3, 4 anything actually. Okay. Now, once you find a good search direction, then you have to go something, I mean some step you have to go, or some in that direction we have to move something. Okay. So, in other words, our initial value or whatever is the updated value has to move a little bit in that particular direction. Okay. That means x k plus 1 can be updated this way, x k plus alpha times p k basically. Remember, p k is of same dimension as state actually, or the again and again I talk about state because x is a state variable in general, but if in a free variable sense, whatever is a free variable in that particular direction, it has to move actually. Okay. So, alpha I mean, and typically alpha has to be a positive number, because you do not want to go in the opposite direction. You got a direction and you have to go in the same direction basically. and you keep on doing this and repeat this procedure 2 and 3 until convergence. Okay, you have to keep that, because also why it is necessary, because the search direction happens to be very local. That means the direction does not remain the same direction as you take a baby step in that particular direction, that the direction of further descent and all that actually happens to be different. So, that is the necessity of doing repeated calculations of this step and step 2 and 3 actually. Okay. If the direction remains to be unique, that means you really do not have to search other directions and all, you do not need to do all that. However, because it is very local property, you have to keep on doing this iterative search, and finally, you will arrive as a convergence thing, and convergence can be checked something like that when the cost function does not improve further basically. Okay. So, j of x k and j of x k plus 1 both are roughly same actually. Okay. Subject to some pre-selected tolerance value and things like that actually. Okay. Sometimes people use relative thing also, they divide it by norm of j x k, and that has to be some percentage quantity now. Okay. That percentage happens to be, let us say, less than 0.1% and all, you can stop actually. Okay. So, there are various ways of doing that, but one way of doing that is just looking at there is no further improvement if I whether I take x k or x k plus 1 actually. That means, x k and x k plus 1 are kind of giving me the same value. And also another way of having convergence is just to see these two values together along with this actually. Okay. You evaluate this and also make sure that these 2 points are not separate by a large distance. It may it can happen if the function happens to be having like, let us say, 2 optimums and all that, like multiple optimums and all of the same value, which is again typically very rare, but it can happen. Okay. Now, for example, like if I just can show something, then the function happens to be something like this, then these two are same values actually. Okay. I mean, I do not know whatever is that x is. Okay. X and f of j whatever. Okay. And it happens to be the same value. Okay. And then these two values are almost the same, and but the distance is large actually. Okay. Then you have to select which one is your optimum point and all that actually. But those kind of situation happens at a very rare case, you do not have to worry so much about those kind of things actually. So, all that it happens is, okay, if I will continue the process as long as I do not see some improvement and all that. Whenever I see this property having, then I think, okay, this is a converse value and all that. So, that is the whole idea there. Start with a meaningful guess value, find some search direction, go a little baby step and repeat the procedure again and again until convergence actually. Now, the whole idea is how do you find this pk, that is the more important thing actually. Okay. So, let us see that part of analysis. So, again going back to the Taylor series sort of ideas, we have j of x k plus 1 can be expanded around j of x k, okay, and this is the relationship what you have actually. Okay. J of x k plus 1 is nothing but j of x k plus gradient of j transpose times this error plus higher order terms actually. Again neglecting higher order terms, we can approximately make it equal, this minus this equal to that, and hence we can solve this. Okay, or in other words, x k plus 1 minus x k, remember these two are nothing but alpha p k. So, I can put this alpha p k here, okay, and alpha is a constant number, so I can have it here, and hence that p k, if I get this direction actually nothing but that. Okay. Why? Because if I select this p k to be exactly same as what I am having here, then this error, this whatever j of x k plus 1 minus j of x k will be a quadratic quantity, okay, with a negative sign basically. Now, this is again a negative sign, remember that. And if I happen to select this, then it happens to be a negative square sort of thing, and hence this is guaranteed to be less than 0. Okay, that is the whole idea there. And what it gives us? It gives us p k as a negative gradient of j, I mean negative of gradient of j basically. So, that is the direction of steepest descent actually. Okay. So, if you happen to take it that way, then you go along the steepest descent direction sort of thing. So, this will guarantee that these two difference j of x k plus 1 minus j of x k is strictly less than 0 basically. So, that is the whole idea why you select this actually that way. Okay. So, once you select this, what is the algorithm there? You have to just once you select this, this is the algorithm there. So, x k plus 1 is nothing but x k plus alpha times p k, where p k happens to be that actually. Okay. So, let us say as it is that, and you can proceed further in that way. So, pictorially speaking, one, if it is the x k is a scalar quantity, then it happens to be, okay, suppose it happens to be your guess value somewhere here, then the gradient thing is somewhere negative. You remember this function, if locally it is negative, and hence you have to move in the opposite direction of that. So, you move a little bit towards in that direction actually, and if it happens to be here, then your gradient is positive, the slope gradient is okay. In this case, gradient is slope, so it is easy to see that gradient is positive. So, you move in the opposite direction again. So, if you start here, you move this direction, you start here, move that direction, and ultimately you converge somewhere where the gradient is 0 basically. So, that is all that, and I have taken this kind of couple of diagrams from this particular book, but they have some little bit different notations here. So, whatever you see as f is nothing but what you consider as j and similar things actually, okay, and small j, okay, and the k sort of thing what you are doing actually. So, just make sure that the notations are not forgotten actually that way, but otherwise the concepts and explanations are taken from this book actually. Anyway, so now coming to the some idea what is called as line search. Okay, the whole idea here is we got this particular direction. So, why taking a small baby step and forgetting this thing actually? Like you can continue searching in the direction as long as the function keeps on decreasing. Okay, that's the whole idea there actually. You keep on searching, expand little more and things like that, and keep on doing that. In other words, make this pk, I mean the travel along the direction of pk, that means alpha, as much large as possible actually, okay, and which will guarantee that the cost function keeps on decreasing. I mean, so some point of time if it keeps on increasing, then it is no point in taking that any larger actually. It will go up to that point where the function keeps on decreasing actually. That is the whole idea of line search actually. So, how do you do that? The concept is again easy. What you have to, let me explain this. First, you have to find some solution here, some value, and then we have found a direction anyway. Okay, so using that direction, you find two values now. Okay, and the one okay, this is a point where the function has a value, and you got a direction. Okay, so using that direction, you have another value. Okay, and don't stop here. You keep on doing that. Okay, find another value where the function is greater than this fellow. Okay, that means greater, lesser, and greater sort of thing actually. And if it happens, then you can actually think that okay, the function has to have take a turn somewhere to go there actually, right. The function keeps on, okay, this is the true function anyway that you want to optimize. So, let us say this function keeps on decreasing, and at some point of time it has to increase anyway, because this function is greater than that actually. So, that means if it is a greater, lesser and greater sort of ideas, then I can actually fit a parabolic curve between the two, because between the 3 points, because parabolic has 3 free variables, a0 plus a1x plus a2x square sort of thing, x square sort of thing. So, I need 3 points. So, I got 3 points, and I will fit a quadratic function using these 3 points, and then find out the minimum point of the quadratic function using the closed form solution, because now we know that actually any parabolic function, if it is a0 plus a1x plus a2x square, and then minimum of that particular function we know very well actually. Okay. So, we will go up to that point. Okay. And then we will see, okay, now here is a candidate solution, and then remember this function takes a shape like that. That means the true minimum lies somewhere here. So, by simply doing a little more math in the background, what we are doing here is we are actually going in one step very close to the true optimum point actually. Okay. That's the whole idea of doing that, and if you apply this algorithm to couple of times, you may converge actually. So, it has a very fast convergence property sort of thing. So, that is the whole idea of line search. So, telling in English words, first of all find 3 guess values of p such that there is up down up behavior. Okay. Then fit a quadratic curve, okay, and find the minimum value of the quadratic curve. I mean, it is not the minimum value of the actual function actually. You got a quadratic curve which approximately represents the behavior. So, find the minimum value of this quadratic curve, okay, and then update your value to that particular point actually. Okay. And that point again you find a new direction and things like that, and then repeat the procedure there actually. So, remember the direction is very local property. So, we may not be able to deal with the same direction anymore actually. Once you go there, you can find a new direction and continue the same procedure right there actually. Yeah. So, that is how this the steepest descent and line search method is quite popular actually, and one easy way of mechanization, and a very intuitive procedure as well actually. Okay. All right. Now, coming to the some other method what is called as a kind of Newton's method and all that, it goes a little bit further, and remember the first derivative or first gradient, I mean the gradient of j has to be equal to 0, right. That is what we know from as a necessary condition of any free optimization, we know the gradient has to be equal to 0. So, if it is non-zero, we will try to make it 0, I mean that is the whole idea there actually. Okay. So, again we will go back to the function expansion, but we will not expand the function per se, we will expand the gradient of the function here. So, it is actually a little bit more intelligent way of looking at the problem actually, because we know that the gradient has to be ultimately equal to 0. Okay. So, we will analyze the gradient of the function and expand it further in using the Taylor series actually. Remember, it is a vector function now, but vector functions can still be expanded in terms of Taylor series anyway basically. Yeah. So, use this vector function and you expand it using Taylor series around the point x k. Then what it gives us? It gives us the first term plus the second term and all that. Remember, second term itself talks about a Hessian matrix now basically. Okay. So, obviously, this gives us some sort of alpha p k interpretation, this part of the thing. And what is our aim? Our aim is to make it equal to 0. So, we will find an x k plus 1 in such a way that this gradient value del grad j at x k plus 1 happens to be 0. That is the whole idea actually. So, if this happens to be 0 and I neglect these higher order terms, then this equation is approximately true, and from here we will directly solve what is p k actually. Okay. So, p k gives this direction, such direction, we can just solve it. You take it to this side, it will give negative gradient and all that. Okay. And then this inverse, and which is happens to be 1 over alpha, and if you define 1 over alpha as beta, then this gives you some sort of a direction basically. Okay. So, again this once you get the direction, you can bring in the concept of this line search and things like that. Okay, that this line search is independent of this kind of ideas there actually. So, you find a direction utilizing the fact that necessary condition tells us that gradient has to be 0 actually. Okay. But remember, this is all true for free optimization thing. The moment is a constant optimization, this gradient vector need not be 0 actually. Now, we have to talk about a gradient vector of a augmented augmented cost function, and that has to be equal to 0 and things like that. Anyway, coming back, this is a very, I think, in a kind of intelligent way of doing that, and again Newton has always been intelligent actually for whatever it is. He is a great mathematician and tried to kind of simplify many things actually that way. So, this is all the way coming from Newton's kind of ideas. Then it goes through like that. So, we can find a search direction very quickly using this thing. The advantage is it gives us fast convergence, and the drawback, associated drawback happens to be this one, because this is a matrix now, and you have to compute an inverse of a matrix, and matrix inversion is not computationally simple. Okay. In general, if the dimension is large, then inversion needs some certain amount of computation before going there actually. Okay. So, that is the thing, but nowadays okay, that is not a major issue. We can talk about matrix inversion rather easily actually, because both numerical algorithms are available as well as computers are fast. So, using both of that, I think this is not a very major issue, unless this dimension is really huge, something like 1000 by 1000 and all that, then it becomes a big dimensional problem and all that. But in our control synthesis problems and all, it will not run into that kind of issues, unless otherwise we talk about flexible systems. Okay. So, we will infinite dimensional systems and all that, which in this course we will not talk actually. Okay. Now, again coming back to the same idea, how do you handle this equality constraints now? Again, as I told you, formulate this cost function, okay, j bar equal to this one, and then try to interpret this as a free optimization with respect to x and lambda. So, carry out the same algebra, okay, you carry out the Taylor series with that same thing, but you have to now cater for lambda variables as well. So, now if you talk about that, it is error in x and error in lambda as well. Okay. Now, this particular thing, this particular thing is evaluated at that, and you can expand that j bar. Okay, j bar is nothing but that actually, it is a function of j and lambda transpose f. So, I can j bar, I can put it and write it that way actually. Okay. That means, j bar of x k plus 1 lambda k plus 1 minus of that, if I do it here, it gives me something like this actually. Okay. Okay. Why? Because ultimately this particular thing is nothing but a constant equation, this is 0. So, this is not counted actually, this term does not contribute actually. So, this is gone and you are left out with something like this actually. So, what does it suggest? Again, we need to decrease this, and this is something like alpha is a positive number and this into this. So, obviously, p k has to be negative of that actually. Whatever you see here, if you just select a negative of that quantity, then you are guaranteed to get a negative square sort of thing actually. That is the whole idea there. So, that is how we get the p k, but now p k is a linear combination of this gradient as well as that gradient, and coupled with this lambda k and all that that way. Now, this has its own geometrical interpretation and things like that. So, in general, again this notational incompatibility will be there, but ignoring that for a second, and I think that you can correlate that rather easily. So, the f turns out to be j and things like that way. So, what happens here? If you just look at the expression here, the search direction is negative direction of these two gradient vector. You first you take these two gradient vector, formulate a linear combination of that, okay, that will give you some direction actually, and negative of that direction happens to be your search direction actually. Okay. Now, another interpretation, how long will continue? Will continue until this fellow happens to be 0, very close to 0 or 0. Then if it happens to be 0, then what is the interpretation? Interpretation is this one is negative of that actually. That means these two quantities, this grad j and grad f, turned out to be aligned actually. Okay. So, this is what you will see here actually. Okay. Lambda transpose this grad f, whatever direction is that, and delta j, they happen to be negative of each other. Okay, that is how it is actually. So, if you do that, the turns out that at the optimum point these two vectors are aligned, or otherwise you have a conjugate direction sort of thing. This is this idea of something called conjugate direction and all that. So, you have typically have a conjugate direction, but at the optimum point these two vectors will get aligned and you have a kind of opposite direction sort of ideas and all that. So, what it tells you, we can draw this contour plots where this C1 happens to be greater than C2 happens to be greater than C3 and all that. If you start at any point, this point still gives you some sort of a conjugate, these two vectors are not aligned yet, and you continues in your search at up to a point where these two vectors are aligned. Now, when it will be aligned? When it is a tangent vector to this particular curve actually. So, you kind of proceed through that up to that point where this direction, if I talk about gradient of f, okay, whatever direction, happens to be a normal, I mean with respect to the tangent vector. So, these are geometric interpretation and all, which is numerically they are much more meaningful, but in this particular course you can just remember that P k happens to be like this, and you can keep on continuing your search until this quantity goes to 0 basically. P k itself is 0, that means there is no more search direction actually that way. So, again more of that explanation and all you can see it in this particular book. It is a typically good book for dynamical systems optimize. That means you talk about dynamic programming and all in detail actually here. Now, before I stop this lecture, I will also want you to introduce to this fmincon function of the MATLAB, which generalizes, which embeds all these and much more. Okay, there is various numerical schemes, conjugate gradient directions, all sort of things actually, and it talks about a generic way of solving a minimization problem. F of x is a scalar which can account for all sort of constraints. You can talk about negative less than equal to 0, you can talk partly 0 equal to 0, you can talk about states these free variables getting constrained both sides, you can consider some linear equations getting constrained, inequality sense as well as equality sense. So, all sort of constraints that you can think of is all embedded here with respect to this particular function to minimize. So, I will not talk about too many details of that, but MATLAB itself has a help function actually. If you go to that help, they have a documentation, there are additional documentations available, and this particular function happens to be very popular worldwide actually. So, it is not extremely efficient function to use it in online applications as far as control thing is concerned, but no matter what, it gives you a lot of these constraints getting embedded here. It is a very powerful technique, and various algorithms also you can select within that actually. So, using that you can I suggest that you solve some of these examples that we have discussed as a part of these lectures using this function also, and see whether that is getting there or not actually. That will give you some practice and some hold on the function, and I suggest that all of you should become very comfortable using this function actually. So, with that I think I will stop this lecture, but before that again these are the references and anybody wants to do further you can study further actually. Alright, so let me stop this lecture here. Thank you.